micron. The resolution in terms of the wall quantities before the flame, obviously. This is the grid size, and this is the cost. So as you see, I mean, it's not something you can do on a parametric fashion. And interesting, this is a non-reactive simulation, so a mixing of the fuel scalar into the cross-flow air. And what I show here is, so C is the hydrogen. The other day we were talking about counter gradient diffusion, turbulent diffusion, and look at this. I mean, the blue, green, red and green regions are regions where the gradient diffusion is wrong. So when this value is negative, your RANS or LES code assuming gradient diffusion would be wrong. So it would predict different mixing.
Counter gradient implies that diffusion coefficient term changes sign? Or
yes, yes.
Or maybe not contribution to flux. Not proportional to gradient, who knows?
Well, yeah, yeah.
Because it's not molecular flux, it's turbulent flux, not the same.
Yeah.
Effective velocity, something.
This is a result of calculations? Or
Yes, from the DNS.
DNS.
So you can you can calculate these terms exactly and find where they are negative. So I mentioned GEG as a report that is public about RANS simulations of jetting crossflow for flame holding studies, and that was a report from 2005, and they said that by 2000, in this report, they mentioned that by 2007 they could have a hydrogen burner for burning in RPM mode. They still haven't done that, and I mean, I'm not sure that this is the main reason, but certainly if you do the assumptions that are completely wrong in your model, in your mixing model, you would get different results.
So what's the reason for that? Yeah.
What's the reason for that? What do you think?
There is a reaction if there is an additional physics, then we can explain through that physics, but this is simply not
non-reactive, yes.
So why are we seeing counter gradient?
Turbulent thermal diffusion, for example.
No, but this is
one of the possible explanations.
To be honest, I'm not sure.
So where does this occur inside the boundary layer or outside the boundary layer?
So the boundary layer is the turbulent boundary layer of the flow, of the cross flow, stops about here. So this is a consequence of the mixing of the hydrogen. So this surface, the white surface that we see here is the isosurface of 10% mass fraction of hydrogen. So it's a marker of the average position of the jet. And you see that these regions with counter gradient diffusion are just around this. So it's a kind of mixing. Yeah, there is a strong counter gradient.
Is there a strong special gradient in those regions?
Yes, yes. There is a strong special gradient.
So what is the density difference between this jet and crossflow and the ambient fluid?
So let me recall. It is nearly okay. The air is 0.44,
yeah.
and fuel is something I believe 0.3, something like that. Yes.
When you calculate this flux,
Yes.
no, on basis you made a simulation. I'm sorry for my stupid question, but nevertheless, have you extracted large scale circulation from total velocity? You should average before this
Yes. So this is, I have the average velocity, okay?
And
the average velocity field.
difference between actual.
So I subtract the instantaneous value to obtain this, and then I multiply them. and then I average them.
Just no problem.
So it's exact like this.
So and you calculated flux of mixtures. You see this
Yes.
is just from the end,
Yes.
and obtain that it's negative.
Not the flux, eh? This divided by this.
Okay.
Okay, so this is the gradient of C mean, of the mean. C is hydrogen, okay?
Yes.
C is hydrogen mass fraction. So the gradient of C mean in this direction, so this divided by this, it's negative. So and this is D, what you that you have in the
Minus D.
in the
Yeah, I
gradient assumption.
But dc over dx was always positive.
No. That
Ratio is
that I
negative.
don't know. The ratio is negative. Okay.
Only the ratio negative.
Yes.
Okay.
You can say it's very clearly seen that another work also you can show that you have this countergraded negative, what you call negative here, parameter. It's when you have large-scale vortices, and you can see really where they are. You can identify. You have, for example, blue is when you start to have this bottom bound layer and the shear layer coming up.
Exactly.
The red one, which is the vertical one, when you start to see the also shear layer, but also you have these vortices that come from this
From the side, yeah.
vortices start going up.
And the green region, I can tell you,
Yeah, it is the
I
component.
haven't. Yes, I haven't shown. Usually, I show other two figures in which I clearly visualize that these regions are quite collected in some large scale vorticity pattern. So I usually show from behind this figure from behind, where this green region is really concentrated right in the shadow of this plume. So behind
In the edge of
Yes.
this, that's what it should be. Quite another question. Did you look at two scales, only one? There's two scales with different molecular specificity.
no, I just looked at hydrogen.
One scale.
Yes.
So which one is not a gradient?
Mhm.
Which one is not a gradient?
Oh, well, what I visualize here are the regions where there is counter-gradient diffusion.
So this color means not a gradient.
Yes, in X, Y, and Z.
And do you have any information about the
I thought that
temperature?
is gradient.
Hmm?
I thought that would come up with a gradient.
What do you mean?
If you write and then you have this. So if it's counter gradient, then this would be positive.
Well, this, what you have.
There is this.
Yes. No, this is counter-gradient.
Yeah.
Yes.
Do you have any information about the distribution of temperature in the regions where you calculate this flux? Mean temperature, mean temperature.
Okay, now wait, okay. This, I have to also, you remember that the hydrogen jet is cold compared to the approaching hot air. So here you have actually two things going on. I mean, the scala that for which I did this is hydrogen, but it's not exactly the same as temperature. Of course, yes. So you cannot really mix these two.
Yeah, but just there can be contribution to the flux of the mixture, turbulent flux. Also, there can be
Yes.
a contribution due to the gradient of
Yes,
temperature.
yes.
And also, there can be contribution due to the gradient of another species, another object admixture,
Yes.
like a mutual turbulent diffusion.
Mm.
Yeah?
Well, what I'm showing is that if you use a model that for this mixing problem uses the gradient assumption, you would get, in these regions, you would get an error. That's the only... I know that maybe there are other factors that contribute this, but
Yes.
nevertheless, if you use in your model this assumption,
Yeah.
well, it will not
Okay.
work.
you can compensate for this. You have the generalized gradient diffusion model where you have the Reynolds stresses are not expressed as a then you can, it's good for jets. I'm not sure if it's working everywhere, but it works at least for jets.
Usually it's very dangerous to have negative diffusion coefficient. It's very dangerous, so it should be checked
From a molecular point of view.
what's the reason.
So this is another plot from some experiments. This is a scalar, so the hydrogen scalar, and some LES from Alston and some RAMs. Different results here for the same, for literally the same case. Okay.
By the way, LES should be possible to predict the counter gradient diffusion.
At the fine scales, you assume.
No, not on the fine scales, perhaps, depending on the model, but why not on the. I don't see that it's impossible to do it with LES.
Yeah, I mean, this
So the last
computation was.
conclusion with
This
the last
computation.
scales
This
and from these structures. So LES should be,
It
I
should.
think, possible to.
Anything okay?
Yeah.
These results, the black circles here, are from an LES done with Fluent at Alston.
Yeah, okay.
That's,
Then you
I
don't
mean,
know what you do.
yes.
It can be anything.
Okay.
Yeah.
So, oh yeah, perhaps you can do better. Well, the point here is that also the experiments, if you look at the literature in this field, there is a quite wide scatter for nominally the same experiments. And this is because these trajectories here are quite sensitive to the boundary condition. So if you change the boundary condition a little bit, you get a big change in the trajectory.
That's why I asked you about the shoulder.
Yes.
Anything that you do there.
Yes,
changes the-
yes. Yeah. So, going to the reactive case, we have seen, first from the instantaneous picture, we could see that the black lines here are the maximum, high heat release regions. So this is a vertical cut through the jet in the mid-plane. And you can see that there is these flame tongues that are slipping through the vortex shedding. So in the region when there is a lot of mixing and strain regions where then fuel and oxidant are strained and can mix faster. In this region you have the strain slipping into it. So this was one of the first observation, and then we tried to look further into it. And to do this, we started, this is a kind of ongoing work, we started to look at this PQR, flow topology, in which the flow field is post-processed to extract these 23 levels that characterize the flow depending on the local strain or compressibility condition. So you have that, in this case, the black lines are the flame progress variable for 4 values, and we could see that the green regions, which are the strain regions, very often these black lines are close together, so they represent the thin flame, while the regions in which we have orange and yellow, these lines are more far apart from each other. So this is the topological classification from Chong and Perry and Cantwell. You can have a look at this if you are interested. What we did is that we tried to look at the details of the vortex shedding regions and try to correlate these two. So, like looking at flow topology at the Q invariant, which the Q invariant is another method that can give you for positive values, compressive vortex region, while strain region for negative values. well, this is entropy and the heat release. You see this tongue, the flame tongue, that it's in the strained region. It's co-located with the strained region. So doing all this in a statistical way and averaging conditionally on mixture fraction, for the progress variable, you can ask, I mean, this is a non-premixed flame, how do you find the progress variable? It's not automatically given. So we used this formula thinking that the product water is conditional on this. So we can see that in the green regions are the strained ones and contain heat release, but not the top values, while the gradient of the progress variable that indicates the flame thickness, in a sense, is very well correlated with the green region, the green strained regions. So some comments about this. So the regions where the Q invariant is below zero, so strain dominated, are found outside the center of vertical structure and within the arms, where the flow classification is the N, well, this one, NSSU. So non-saddle, saddle, unstable. So I'm referring to, if you think about this vortex here, so the green regions between the arms of the vortex. This is also the region where the heat release suggests that the flame is being wrapped up and strained by the vortex. The most upstream point of the flame is in the vicinity of where the breakup of the flow structures begin, so the breakup of the vortex shedding. The flame front is most diffuse and penetrated by small vertical structure in the breakup zone. So if we look back at this, you can see that here there are quite large structures of the vortex channel in the shear layer between the jet and the cross flow. But here there are a lot of small structures that are following the jet breakup. And this creates a much more diffuse flame in this region. So the flame front appears thinnest in the region where there is a contiguous region, so the green part. So, and while this region is the configuration is the quintessential notion of flameless, the diffuse flame penetrated by small flow structure is consistent with the notion of the broken reaction zone. So what I'm trying to say is that this flame is very complex. You have some regions where you can describe the flame as a flameless, but other places where this model would fail. So if you use a model, a flamehead model, you probably will not be able to represent this flame, while perhaps if you use a model that can address both mode regimes, as the model that you showed us the other day, perhaps you will do a better job here. Perhaps.
Can you test it?
Hmm?
Can you test it?
Yeah. Yeah. So this is just an animation of the simulation where I show temperature, the color field, and the heat release by the lines. You can see that the vortex shedding starts at a certain distance from the jet, and then you have the flame tongues slipping into these regions with a very consistent time interval here.
But now, why does the flame just start with these little circles?
You have probably a big
It just starts there.
a big vortex carrying heat, hot gas back.
Mm.
That's the shear layers.
And also look at the large scale regions here. You know, there are this in the
But it
jet
can't
cross
carry
flow.
the gas back.
It has to be, otherwise it's cold.
Are the velocities actually negative? Are the gas velocities going that way?
No, it's in that direction now.
No, but I mean, at any instant of time, does the gas go this way? Do you have recirculation such that there is negative velocity in the
Here you mean, in the
airflow?
vortex shed.
Right. What I'm asking is, how do you get the hot gases to come upstream and magically appear there? You know what I'm saying?
You are
Right
saying
there,
here.
see the little greens just started?
Well, but you know, this is just a mid-plane, so there are vertical structures that wrap around the jet and that can bring the flame from the side.
And the jet is shielding
Inside.
the mainstream. You have no.
I mean, there is a region
Okay.
of low mean velocity here. I will
Okay,
show
so
it
then
later.
it's not recirculation, then it's just the flame is somewhere on this three-dimensional surface, and then it sometimes goes to the bottom.
Mm.
Well, yes, fluctuation in spin lasers actually.
But also, I mean, the velocity here is 240 meters per second vertically.
Yeah.
But when these vortex are shedded, there are a large variation of
Yeah.
velocity. So near, just behind the jet here, there is a shear layer with low velocity regions. So in this place, the flame can propagate. In fact,
Yeah, that's what I'm asking. Most people would think that there is a premix flame right at the base there, maybe a triple flame. Do you think that's
well,
true
you
or
know,
not?
we have tried to use this Takeno flame index
Yeah.
to see if we could classify this as premixed or non-premixed. It's very tough.
Yeah.
It's very tough. This is OH radical mass fraction, so
Yeah.
it's just the same movie, and the lines are the oxygen. So there is no oxygen that's in the jet,
Mhm.
and the rest is. So as you see, there are a lot of small structures in this region, small turbulent structures, and much larger ones here. And then you see sometimes, I could have shown this also for the temperature, some legs going down here, and these are the wake vortex as they are defined, that bring hot gas towards the wall.
Those are existing also in cold frames.
Yes, they are typical of the jet and crossflow.
The other thing you see is that, just like we see in the experiment, that the flame is mostly on the downstream side of the jet.
Yes.
On the other hand, there has to be mixing on the upstream side of the jet, because there's pure fuel in
Yes.
the middle of the jet and there's air on the outside. So there has to be a stoichiometric contour on the upper surface in which there's no flame. So do you argue that that's strained out? or
Strained,
some- yeah,
yes.
okay.
I would say so.
Okay.
That it's,
That's-
and you see also, look at what happens here. Look at this
Yeah. Yeah.
this non-reactive bubble here.
Mhm.
I mean, to be able to say what's going on here, it's not very easy from the instantaneous.
It might be too
fields.
rich though, because
Yes.
it's
Yes.
the edges of that might
Yes.
be so flammable.
And
Do you also see what the JAXA people have seen? Where you have a lean premix flame and then rich premix flame in the center and then surrounded by diffusion flame.
well, kind of. I will show some average field later, and I can comment
I
on
have
that.
a question.
Yes.
In what place here you found a negative diffusion?
No, I did not.
Not here.
I did not do the same computation for the counter gradient diffusion for the reactive case
Oh,
yet,
I see.
but I can do that. Obviously, that was only no reactive. The other thing.
It was non-reactive.
Yeah. So okay, we have seen enough of this. So this is DLR is doing is involved in the same project and is doing some leaf of this of similar flame, not exactly the same. There is not the same ratio of fluid, but this is just to show that this large extinct. So this is virtually the same quantity we were looking at before. Okay. You will see in the animation that there are large regions of non-reacting bubbles, either to reach or somehow extinguished. obviously the time resolution of this is not the same as the DNS, so you cannot really see the details of what's going on here. The DNS was very clear in this and very helpful. So this is, well, sometimes you will see these pockets of black or no signal for a similar flame.
Also 1 diameter jet?
2 millimeters.
Into here it's 2 millimeters.
Yeah.
And it's, you have a much lower momentum ratio.
Yes,
compared
yes,
to yours.
it is. So this jet was, I think, 150 meters per second instead of 240. So looking at average fields, to get some more, perhaps, some more quantitative information. This is the velocity field. You see that there are two, well, this is the boundary layer. This is the, how do you call it, saddle point, or where the streamlines divide. So the low velocity region ahead, and then you have this recirculation region behind the jet, and then you have this. This is a kind of low velocity region away from the wall, so there is not much heat loss here. It's just behind the fuel plume, so it's probably fuel rich, and low velocity. So where better place to anchor a flame? So, and you see the lines are the heat release. So the maximum average heat release is co-located with this low velocity region. And so as a part of this parametric study that we did for many other configurations, non-reactive, we are trying to avoid flame holding. We are trying to avoid this region, because this region we see also in the non-reactive cases. So our guidelines are in the direction that when we manage to avoid this cannot be really avoided. But when we manage to avoid this, then we have probably a safe injector. So this is the temperature field. You see, this is the low velocity region now marked with the ISO line of 25 meters per second. So there is this small blob.
You know, you showed low velocity regions upstream of that too. In the previous one
Yes.
was a line of 0.1.
Yes.
But that's highly strained.
Strained.
And,
Yes.
and so
Yes.
it's more than just
Yeah.
it's velocity.
Yeah.
and
Well, okay. You could see the same here. This is a low velocity region. Why is not anchoring here?
Yeah.
We were in fact afraid of
Right.
this, that the flame could anchor here, and then there is not much to do. But here, this is cold, and in fact there is not so much fuel here.
So your
On
water
average.
temperature is 300 in your simulation.
Hmm?
What?
Wall as the same as air, so 750. So when I say low temperature here, I mean that you would have a flame here, it would quench probably because of the heat.
There's no fuel. That's
Yeah.
the most-
And there is no
that's
fuel.
the
Yes.
most important. Did you try to compute the average or the turbulent phase speed? From the data?
Where?
For example, now you know where flames anchor to this area, so you can compute some kind of you have the
Okay.
you have the flame lines, and you can
Look,
already compute.
okay. Look at this.
Yeah.
We have a flame here, on average,
Yes. No, but
and there is a velocity of 25 meters per second.
no.
So what you make?
No. But you have the flame front. You have the instantaneously.
Yes.
So and then you start to follow it, and then you have.
Yeah, the displacement speed. Yes, yeah, we can do that. I haven't done this yet,
That's
but
not-
we can do that. Yes. It becomes a little bit arbitrary depending on where you are. How you define the surface?
Orthogonal is the surface. That's what you
Yeah, to which surface?
to itself. When you have the normal, you compute the normal of the surface. You have the lines that you showed. It's progress variable lines.
Okay,
How will
okay.
we
So
define it?
define on the progress variable as I did. Okay.
For example,
Yeah.
you have the velocities, everything there.
So the temperature field and the OH mass fraction, so all agree on the most upstream part of the flame anchored there. Here we see the average heat release and these two counter-rotating vortexes. The interesting thing here is that this is so the jet is at 5 millimeters from the inlet. So this is 2.5 millimeters. Basically, this is in the here. Okay, so 5, 7.5 here. And you see the highest heat release is between the vortexes, between the counter-rotating vortex pairs.
This is large scale vortices?
Yes.
But that's how I have a problem there.
Yeah, it's not symmetric.
No,
No?
symmetry is one thing.
Yeah.
Because if your reasoning was correct, or my reasoning also, that you have the concentration is dependent on this large scale, fuel distribution dependent on large scale motion of the vortices. So you would expect that you would have the flame around this structure,
Wait, next
and
slide.
then it's going to be in the middle. Okay.
Look at it. So what the interesting thing that I want to point out is that in the beginning, at the most upstream flame location,
Okay.
the flame is anchored in between the vortices. But then, just to some diameters downstream, then you see that the vortex has some blue contours, and perhaps this is not the best contouring use, but you see that there are some orange regions that go around. So at this position, what you are saying is
So I
happening.
expect
Yes. So, but the flame doesn't look like, if you look it from above, it does not look like this. Okay, it looks like this,
Yeah,
and
two
then
separate.
these two vortexes are here. Well, actually, yes, like that. So, what the JAXA people noticed is perhaps that they have no premixed flame here at the top, or at the most upstream position, and a premixed flame around here. Perhaps I'm not sure you are referring to a similar configuration.
Well, that sounds reasonable.
Yeah. Okay, so flame holding in near field or the fuel jets appear to be closely related to the vortex shedding, as we saw, and not to flame propagation in the boundary layer. So this was what we were afraid of, that the flame could anchor, in fact, very close to the wall, where there is really not much we can do for the design. So further, this simulation was completed in December, so we did not have enough time yet to explore all possible implications, and I'm available to get suggestions and interests. And
If you want to move the flame down,
Yeah.
make the whole ellipsoidal with the main direction and the flow direction.
yeah, this is what we are looking at
Move it down.
with the parameter study. And
Because
you
if
know,
you
by
do that-
injecting at 70 degrees, for example, this low velocity region where the flame was anchored disappears. There is no more. So, but I mean, the problem is not. It's an optimization problem. So you have to take into account different processes. So when you inject 70 degrees, you avoid the flame anchoring, but you also mix worse, because it will take longer time before the fuel
And that's
mixes.
the real venom is not working.
Yes. Yeah. So it's not.
Try with the ellipsoidal. That's better.
Yeah. So yeah, further work includes investigation of the boundary layer movements, nozzle shape, injector angles, and so on. Yeah, and it will be presented in the sheet. That was it, I think.
small comment
Yes.
related to the first part.
Mm.
Okay. In principle, you define such flux for a mixture as one.
Mm.
This flux, turbulent flux, contains three terms.
Mm.
This is usual turbulent diffusion.
Mm.
If you have also gradient of another mixture,
Mm.
there can be contribution due to the mutual turbulent diffusion,
Mm.
and there can be also cross effects due to the gradient of temperature.
Mm.
So you divide this expression by gradient of C1.
Mm.
Okay, so this is,
Mm.
and you say that in principle this expression is negative.
Mm.
So there are also
Yeah.
two reasons
Mm.
which yields you to this value.
Yeah, well,
So if you have information about this
mm.
and about this,
Yeah.
you can answer the question.
Mm.
If really this quantity is negative.
Yes, yes.
Well, it's very dangerous to have
No,
negative.
but you understand my point.
Yeah.
Is that other models make
Yeah.
that assumption. What
Yeah, I
I brought
understand.
there.
You
So,
said
I-
these two terms are dropped.
Yes.
Yeah.
So if you use that model,
Yeah.
and perhaps you would get wrong.
Just a moment. Is it large simulation, this calculation? Am I right?
No, DNS.
Even DNS. This calculation is not model in some sense, it's result. Of course, maybe this coefficient equals 0 in your real system, but maybe not. It's an interesting question. What's the real value of this coefficient? What we observe in our laboratory without any chemical reaction. There's at least last term not equal 0. I'm pretty sure that the second term not equal 0 too in presence of chemical reaction.
Well, depending on the size of the different sizes of the molecules, that's because it's the binary diffusion between the C1 and C2.
Yeah, but turbulent, yeah. Turbulent
Right,
mutual
right. But it's the same
yeah.
as molecular. It's the same as molecular.
Yeah, this is similar cross effects for
Yeah,
molecules.
suppose the C1 equal to C2, that's similar molecules, very much
Yes,
the same.
I mean
And it's,
the
it's
contribution. I mean this is
The debate is one.
okay.
No,
I
but
agree.
this is turbulent.
But
It's not the same.
Igor,
Yeah.
I agree with you. What I was trying to point out was that if you do this with Grant's code and you assume that your turbulent fluxes are equal to d times the gradient of the mean scalar, you would do a mistake. That's all. Okay.
I know that Kalgaki has published jets in a cross-flow, just global blowout limits, experimental data. I don't know if anybody has measured the liftoff height of a jet in cross-flow. That's difficult, but I'm just wondering, is there any experimental data you can compare to just for the global? Should this flame be there in an experiment?
Okay,
or will it blow up?
DLR is doing this in the project that has produced these results. Is doing similar experiments because the project is the three of us, so Sintev and Sandia, to the extent we do simulations on their machines, DLR and Alstom. And DLR is doing the experimental part of this.
Okay,
And so the experiments from DLR show that there are two limits. So when you blow at this. So there is the jet, So this is the jet velocity and this the U cross flow. So say that we keep this constant and we start by the low value of this. So low value, no flame. Increase, no flame. Suddenly the flame will be there, increasing this, but it will be I could show you the well, I cannot. If I could show you the POD analysis of the leaf data, you would see a strong, well, a weak mean signal and a strong mode 1 covering the whole flame. So the flame is basically extinguishing and reigniting. So it's a kind of, we are near the lean.
The jet is too low in velocity, then it does not create a strong wake. The stronger the jet is, the more it acts like a buff body and creates the recirculation zone.
Yes.
So, but then if it's too high of a velocity, then
when you increase the velocity further, the flame gets more and more stable. Finally, you get the other limit when the flame is blown off, and it's not there is not enough residence time for the flame to be there. So you have these two limits.
That's one way. Or another way to think of it is that there's a base of the flame is propagating against this high velocity. If it's too high, it won't stay there. It will blow up. Depends on what. But it may be a little bit of both.
That was it.
Okay.
Have you looked at the gradient information in this flows?
No.
Be interesting to see.
Yeah, I mean there is, as Jackie was saying, the data is so rich here. There is a lot of things that are unclear. Also the classification. When I showed this to Barlow in December, where I was at Sandia, and we looked at the curves of mixture fraction against the temperature. They were all over the place. I mean, you could not classify this with any
canonical structure.
No.
So that's really bad.
Yes.
Wouldn't one argue that you should have both mixture fraction and progress variable?
That's right.
This is partially doing it. I mean, that's
Yes.
what your work is.
That's right. And you need to have three gradients. One is the mixture fraction gradient and the progress gradient and the cross gradient.
But again, I mean, the work that has been done for December for the symposium was quite hurry, because this was run in November, so we have not so long time. And now next week, Ray Grout, the guy that I was working with, he will come to Trondheim, and we will keep on working on this. And the guys from KTH here, the fluid dynamics people, they were interested in having a look at this also in terms of the jetting crossflow instability. So they have indeed some modes of instability, and perhaps we could correlate this instability mode of the vortex shedding to the frequency that the flame advances. As you've seen, there is a clear period there that is suggested.
What is draw number? You can say that. I can say 0.2.
Yes. Okay. Thank you.
Thank you very much.
Only 1 hour.
So tomorrow is at
10 o'clock. There is there's a train at 10 o'clock. There's a train leaving at 9:37 from and then you have to change at and then you take the bus number 47.
It's fine.
It's just in time. Oh, yes.
There's a Russian number starts with
Was it again?
Yeah.
Right down, I didn't find my notes.
it's a free
I don't think people would like to know.
That's the translation of it.
I see.
all the way to
So if you know that, yeah, I can do that. Search for inverse diffusion.
there's heat
In
release
that paper, they will
everywhere. And each plane, so they would determine the total.
So the title of the paper is inverse
So one would have sponge release
Yeah.
function
for the reaction.
Now, whenever
Interesting. How many people do you remember name?
It's a Russian name.
how much energy what the beginning began.
Search for inverse diffusion planes.
Here you also should know where the
Inverse
the heat will make you go up here.
I'll find it for you and then send it to you.
This is more difficult because now you have to recruit the entire flight to the very end. Can you do that or not? Too much stuff.
I mean, it requires
It seems the law
Peter's turbulent convection.
You don't know what's in it. If you're looking at just here,
Yes.
I mean, for the data that I have, I can integrate along the plane. But I'm not sure that I will have zero use at the end. So this is
You said that there are three.
Three gradients. Here we have mixed chemical reaction.
okay.
Some situation you can have both. In some regions you only mix. Some regions you have reaction. So you have to explain these three physical processes. Which is
I
not
gave,
exact.
so I will try to answer and tell you.
I was thinking of the same question and I was about to get
Yes,
I think maybe
Ну, если на теплот, и теплот, я тоже знаю,
But there is no extra
идеально психический теплот, там.
yeah, they countergravity is driven by pressure.
either pressure field or heat release field.
Yeah.
One of them has to be there. But in a non-reacting flow like this, I can't see that. But if you look at the subgrade scales, there could be a possibility for that counter gradient.
So,
Even in pure
this
mixed,
actually
people
people
are
turbulent diffusion.
Yeah.
There's a paper in
Velocity.
two
One proportion
theoretical
of
concentration.
gradient total energy.
by one of the
Forget
journalists.
the gradient of total
They have
energy.
reported
Certain
counter gradient.
imagine
Even in
remember
pure
correct.
mixed. But that's in very small.
This
But what you are
and
doing is
so
large scale.
Yeah.
Which is
now gradient is very
I didn't understand the sign. I still don't understand.
I think the sign is correct, no?
No, I think the sign should be the opposite.
You can have
Yeah, of course, coefficients are different. Absolutely. Physics.
I don't think so.
You know.
If you do the
Mhm.
gradient diffusion model, then that what comes out. What you get is flux divided by this gradient.
Mhm.
Then if the counter gradient diffusion is occurring, then the diffusivity has to be negative.
Mhm.
Then the whole thing has to be positive.